Welcome to our video on thinking mathematically, or what I like to call thinking the right way. Let's look at our objectives. So we're going to try to understand mathematical reasoning, see the difference between inductive and deductive reasoning, and then identify arithmetic and geometric sequences, which is really just kind of looking at numerical patterns. Okay, so mathematical thinking is really just a broad term for being able to work your way through a problem systematically using reasoning, right? Inductive and deductive reasoning. And reasoning is just another fancy way of saying, logic and using science and rules and things like that rather than just intuition and what I think might be right. All right, inductive reasoning is the idea of kind of arriving at a conclusion based on observations. So inductive reasoning can be considered generalization in the fact that when you see something happening over and over and over again and you see a pattern, then you inductively reason that that pattern holds. I'll give you an example. I tend to notice on the road when I'm driving, more often than not, a General Motors kind of SUV or truck. So if you look at all of Chevy and General Motors SUVs and pickup trucks, for some strange reason, they tend to often have one of their running lights out. Not the headlight, but the running light, the ones that are below the headlights. And it's almost always the one on the driver's side. So because I've noticed this pattern, inductive reasoning tells me that I can generalize and say that there might be something wrong with General Motors manufacturing that causes the driver's side running light to burn out prematurely. Okay? So that's inductive reasoning. You see a pattern and then you generalize it, right? I've seen it on 100 or so vehicles and I'm going to generalize it to all General Motors vehicles, that kind of idea. So here's another example. So in New York City, it snowed 30 inches during January 2010 and 35 inches during January 2011. Therefore, New York will receive at least 30 inches of snow every January. Does this use inductive reasoning? Well, there is a pattern, and they are generalizing. So therefore, it is inductive. Now, is it a good argument? Probably not. And why? Why does inductive reasoning not work in this case? And hopefully you're all saying, well, the sample size is too small. They generalized from an observation of only 2 data points, right? They only saw snow in 2010 and 2011, and then now they're going to make a prediction. They're going to generalize to all future years based on those 2 data points. It's not enough data. You haven't observed enough to be able to generalize. When you do observe enough and you see the pattern hold over a larger sample size, over a longer time period in this case, then your argument holds water a little bit better. All right, here's another one. Consider the following sequence. If the pattern continues, can you conclude what the next number will be, and can you figure out what the 15th number will be? So you have to look at that and kind of figure out, is there a pattern? So your first instinct might be, okay, well, the first one goes up by 3, and then the next one goes up by 5, right? And then the next one goes up by 7, and then up by 9, 3, 5, 7, 9. So maybe the next one will go up by 11, right? You can look at it that way and think, okay, well, if it goes up by 11, then I think the next number should be 36. All right, is there another pattern that you can see? Well, maybe you notice that the first one is 1 squared, the second one is 2 squared, the next one is 3 squared, 4 squared, and 5 squared. So shouldn't the next one be 6 squared? And 6 squared is 36. You notice how our patterns worked both ways, right? We saw a pattern of adding something that changed, right, each time. And then we also figured out that it's just n squared. And the n squared way is a lot better because both of our ways we can find the next number of 36. That's pretty easy. But if you want to take that out to the 15th, then now you have to go, all right, so I add 3, 5, 7, 9, 11, 13, 15, right? You have to count those all the way up till you get to the 15th number. And that can open you up to a lot of possible mistakes. Whereas when you know it's just n squared, then the 15th number is just 15 squared or 225. So finding patterns is very important mathematically, and it's a very basic concept of inductive reasoning, is finding those numerical patterns. Okay, in inductive reasoning, we can also use a counterexample. It's a contradictory example that does not satisfy our conclusion, therefore making our argument invalid. And the nice thing about counterexamples is we only need one counterexample to prove that our argument is false. Because remember, when we're doing inductive reasoning, we're trying to come up with a generalization that is supposed to work all the time. So for instance, if we go back to that snow thing, we would only need to find one January anywhere after 2010 that had less than 30 inches of snow, and our reasoning would be false. So consider this statement. You must have a degree in computer science to become wealthy in the computer industry. Now, is this a valid argument? Well, obviously not, because there are hundreds of people in the computer industry that are very wealthy that do not have degrees in computer science. Many of the wealthiest people in the computer science industry dropped out of college before they got a degree. Doesn't mean you should do that, but it just means this argument is bad. Now, because we can want to try and disprove it with a counterexample, then we only need to find one counterexample. And like I said, some of the most well-known and wealthiest people, Steve Jobs and Bill Gates, for instance, neither of them have a degree in computer science. And yet they're, well, before he passed, Steve Jobs was one of the wealthiest people on the planet, and Bill Gates continues to be one of the wealthiest people on the planet. So we found a counterexample to our conclusion, and therefore our argument is invalid. All right, let's look at some more examples. Can you identify the pattern in each of these sequences? 4, 9, 14, 19, etc., etc. Are we adding, the easiest thing is to ask yourself, are we adding the same thing each time? So are we adding the same number each time? Or are we multiplying by the same number each time? And if neither of those work, then you look for other simple patterns like, the one we saw where it was the number squared, and then you look at, okay, number cubed, or maybe it's each number times 3 or something like that, and then you start looking for sequences of patterns. Maybe they're doubling it and adding 7, those types of things. So let's look at the first one. Are we adding the same thing each time? So to go from 4 to 9, we added 5. To go from 9 to 14, we added 5. To go from 14 to 19, we added 5. You go, aha, that's easy. We're just adding 5 each time. So if we add 5, the next one should be 24. Simple, easy. Okay, what about this one? 2 to 6 is 4. 6 to 18 is 12. Okay, so that's not working. We're not adding the same thing. How about multiplying? What do we have to multiply 2 by to get to 6? 3. Okay, 6 times 3 is 18. Hey, 18 times 3, 54. Looks like we've got our pattern. And the next number is simply going to be 54 times 3, which is 50 times 3 is 150. 4 times 3 is 12. So you add those together and you get 162. Okay, what about the last one? Well, we add 1, then we add 2, then we add 3. We're not adding the same thing each time, but that seems like a pattern, right? First we add 1, then we add 2, then we add 3, because it definitely isn't multiplying, right? To get from 5 to 6, we got to multiply by a fraction, and from 6 to 8, we also got to multiply by a fraction. We don't want to have to work with fractions. So it's a lot easier to think, okay, well, I added 1, then 2, then 3, so most likely, if the pattern holds, the next one is just adding 4, and the answer should be 15. And you have just now practiced inductive reasoning. All right, here are the solutions. We already did these, right? So I'll go through them kind of quickly. Where we saw that we were adding the same thing each time, so that got us 24. The next time we saw that we were multiplying by 3 each time, so that got us to 162. And as we saw in our last example, we are adding different terms each time, right? It showed us here, talked about how we had to add 1 to 5 to get to 6, and then we added 2 and then 3 and so on and so forth. Okay, arithmetic sequences. Arithmetic sequences we've already seen. An arithmetic sequence is just any sequence of numbers where each consecutive pair, right? So two consecutive terms. So if you go from the first to the second, or the third to the fourth, or the ninth to the 10th, the difference between those two numbers is always the same. It's a big, long worded way of saying if you're adding the same amount to each number to get the next new number, then you're doing an arithmetic sequence. And we've already seen examples of that, right? We saw in in part A, that we added 5 each time to get the next number. So that was an arithmetic sequence. In part B, we multiplied by a number each time. That's going to be a geometric sequence. And then in part C, we added a different number each time, so it was neither, right? So not everything is either arithmetic or geometric. It can be a neither. So the geometric, like I said, it's when you multiply by the same thing each time. And again, we're going to give you some big fancy words about a common ratio and two consecutive terms and blah, 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 blah. Basically, it just means that to get to the next number, if you're multiplying by the same constant each time, and it doesn't have to be a whole number, it could be a fraction, right? You could take something, multiply by a half, get the next number, multiply by a half, get the next, and keep doing that. And that's a geometric sequence as well. Or you can multiply each time by 2.3, who cares, right? Multiply by pi each time. As long as you're multiplying by the same thing each time, it's a geometric sequence. Now, how about reasoning with patterns? These lines represent multiplication of a cell at a certain point. So it starts with one cell, then it goes to 4, then 9 and 16, and so on and so forth. And they want you to determine the number of cells present on the next production. Well, you look at that and go, I can write down the numbers, 1, 4, 9, 16, recognize that all those numbers are perfect squares, 1 squared, 2 squared, 3 squared, 4 squared. So the next one's going to be 5 squared, which is 25, and I'm going to have 25 cells, right? So it doesn't matter if it's numbers or patterns, the idea is still the same. You're looking for, is there a common difference? Are we adding the same amount each time? Is there a common ratio, i.e. are we multiplying by the same number each time? And if neither of those works, then you go to the next simple ones. You know, am I squaring a number? Is it 2 times a number? You're just looking for patterns. And so when they give you pictures, the easiest thing to do is to kind of write in the numbers, right? Instead of looking at these blobs, these cells, you'd sit there and go, okay, well, this is 1, 4, 9, 16. And then it'll help you figure out that the next one is going to be 25. Same thing here. It's a pattern, and we have to relate it to numbers. So if they want to know what happens in the 8th figure or the nth figure, then what you need to do is number your figures, right? This is figure number 1. This is figure number 2. This is figure number 3. And now, look at it and ask yourself, okay, what's the difference? You know, what's happening? Well, I can see here that I have one block on each, you know, kind of wing, right? You start in the middle, and then you have one block on each of the 4 coordinates, if you want to think of north, south, east, and west. And then here I've got 2 blocks each. Here I've got 3 blocks each. Well, there's the pattern, right? Wouldn't the 8th figure have 8 blocks on each of the 4, you know, propellers, if you want to think about it that way? Or maybe you started, you know, adding up all the dots or all the line segments, and you can make a correlation between the number of dots and the number. But basically, you're just looking for a pattern. So now the nth figure is going to have n number of boxes in the 4 directions. And so if they asked you how many boxes they have, well, doesn't this one have 4 plus 1, right? Doesn't this one have 8 plus 1? This one has 12 plus 1. Well, what the pattern is, it's the number, right? 1, 2, 3 times the 4 things and add 1. So it's the number 2, right, times 4 plus 1. The number times 4 plus 1. So if they want to know how many blocks are in the 8th figure, wouldn't that just be 8 times 4 plus 1, or 32 plus 1, or 33 blocks? And if they want to know the nth figure, well, that would be n times 4 plus 1, right? Because you'd have those 4 blades that each have n number of things and that one in the middle. So you'd have 4n plus 1 many blocks or squares, whatever you want to think about calling it. So they're just, answering what we did, because they're asking for line segments and we were doing blocks, right? We could also figure out the pattern for line segments very easily, because based on how many blocks you have, you can figure out how many line segments you have. But you could also figure it out based on just the overall pattern. Okay, so it's all about just finding patterns. All right, deductive reasoning is a process that begins with a commonly accepted fact and then arrives at some logical, specific conclusion based on that given fact. So it's kind of like, we know this to be true, and based on this, we're now going to say that this next thing should also be true. So consider this statement. If you are a mammal, then you have lungs. So how can this be evaluated as a deductive argument? Well, it's got two parts. Determining if you are a mammal and whether or not you have lungs, right? It's got kind of two parts, the mammal part and the lung part. Breaking down the individual components of the statement, we can figure out what's going on. So, part A, right? I am a mammal and I have lungs. So the premise was true and the conclusion was true. And then B would be I am a mammal and I don't have lungs. The conclusion is false. But notice that in B, when the conclusion is false, the argument does not seem to follow logical thought. And we'll get more into this in chapter 3. And what I mean by it doesn't follow logical thought is those two things are kind of not related. And so it doesn't really help prove or disprove anything. It'll make more sense when we get to the whole idea of truth tables. So to illustrate the difference between inductive and deductive reasoning, let's think of the following process. You choose a positive integer, you multiply it by 2, then you add 1 to that product, and we're saying that if we do that, it will result in an odd number. So if we want to evaluate this as an inductive argument, we're going to do it one way, and if we want to evaluate it as a deductive argument, we're going to do it a different way. So let's see how the inductive way works. Well, inductive, remember, is you got to have a pattern. So you see if it holds. Just start with some numbers. Take 3 and do the process. Multiply by 2, add 1. You get 6 plus 1 is 7. Take 6, multiply it by 2, right? Add 1, 13. Take 8, multiply it by 2, add 1. And you can see that all of those come out to be odd. And in fact, the beauty of math is that everything is in groups, right? And when we talk about whole numbers, because this argument said choose a positive integer. It didn't say just choose any number. It said positive integers. So we're taking what are considered the counting numbers, 1, 2, 3, 4, 5, 6, 7, out to infinity. We're not using 0 because 0 is neutral. It's not positive, right? And we're not using negative numbers. And then we're not using fractions and decimals and all that kind of stuff. We're using integers. Well, when we talk about the positive integers, they all live in two groups. They're either even or they're odd, right? It's the only two things that those numbers can be. And so really we just need to check and make sure that all even numbers follow this rule and all odd numbers follow this rule. So we tried one odd and it worked. We tried two evens and it worked. Do you think that's enough to think the pattern will hold? Well, 3 shouldn't be a large enough pattern. But because math is such a wonderful thing, it really is enough. And we could do it algebraically to prove it to ourselves, right? Because we know that every even number is of the form 2n, and every odd number is of the form 2n plus 1. Well, isn't this what it just described to us? Take it, multiply it by 2, and add 1? Yeah, so we can see that no matter what we put in there, it's going to be odd. Now, even if you didn't know those general rules, you could see the pattern after you played around with enough of them. And we can make the conclusion that taking any positive integer, multiplying it by 2 and adding 1 will result in an odd number by inductive reasoning, because we saw a pattern and we generalized. Yep, that's all it is. Now, if we want to do deductive reasoning, we have to kind of go to the algebra. So we're going to let x represent whatever this chosen integer, right? Whatever positive integer is that we're going to choose, and then use deductive reasoning to show that we do, in fact, have this valid conclusion. So if x is going to be the number we choose, when we multiply it by 2, we get 2x. When we add 1 to it, we get 2x plus 1. And so in algebraic form, we know that the result will always be of the form 2x plus 1. And as I told you before, that's the general form of every odd number, right? Because an odd number is always one more than an even, because they alternate. So if you take an even, which is just something times 2, right? Because that's the definition of an even number, it's divisible by 2, so it's 2 times something, 2x. Then you add 1 to it, there's your odd number, right? So there's the general form of an odd. We can see that it works, and we've proven it with deductive reasoning. So we now know that when you take any positive integer, multiply it by 2, and add 1 to it, you will always get an odd number. Do you see how deductive reasoning is a much stronger argument than inductive reasoning, right? Inductive reasoning is, I see a pattern, I think the pattern will continue to hold, and so here is my theory, so to speak. Deductive reasoning is, I think something is true, and now I'm going to prove it using established facts. I start with a given fact, and then I prove that something else is true based on that fact. And that's a much stronger argument. So we always try to use deductive reasoning if we can. All right, last but not least, we can look at another example. Consider the following process where we select a number, multiply that number by 10. Now subtract 25 from that product, then divide by 5. Finally, subtract the original number from the result. Can you determine the general solution using deductive reasoning? Well, it just goes back to that same translation, doing the math. Select a number, call that x. Multiply the number by 10. Now we have 10x. Subtract 25 from that product. So now we have 10x minus 25. Now then divide that whole thing by 5. So we have 10x minus 25 all over 5. And when we divide all this stuff by 5, we got to divide each piece by 5. So 10x divided by 5 is really 2x. And then, of course, 25 divided by 5 is just 5. So there's my 2x minus 5. Now it says, finally, subtract the original number from that result. So we're just going to have 2x minus 5 minus the original number, which was x. And of course, 2x minus x just gives us x, right? So doesn't this whole thing should just equal x minus 5. So can you determine the general solution using deductive reasoning? Yes. You will get 5 less than the original number, right? Whatever the original number was, you will now have 5 less than that. Can we test it with some specific numbers? Sure. Let's use 3. Let's let x equal 3, right? So we're going to start with 3. We multiply it by 10. There's 30. We subtract 25 from it. There's 5. We divide that, that's equals, so not minus. We divide that by 5, and now we get 1. Subtract the original number from it. Subtract 3 from it. 1 minus 3 is negative 2, right? And isn't negative 2 5 smaller than 3, right? 3 minus 5 is negative 2. So it worked for that one. You could try it for a big number too, you know, like 100. And you get 10 times it. There's 1,000. Minus 25 from it, so there's 975. Divide that by 5, so that gives you 1. And then 47 is, 9. And then 25, so 195. Subtract the original number, subtract 100 from it. We get 95, and 95 is in fact 5 less than 100. Okay? And here's all that written up in fancy red letters. All right, that's everything we need to learn about thinking mathematically.